good morning everybody. So today I'm going to do application of Gauss's theorem. Last day we did Gauss's theorem, what is Gauss's theorem and the proof of Gauss's theorem, and also we did electric flux. Okay, so today we are going to do the application of Gauss's theorem. Okay, so just a recap, what was Gauss's theorem? Okay, so we knew that Gauss's theorem, so Gauss's theorem was electric flux linked with any closed surface is equal to 1 by epsilon naught times the total charge enclosed within that closed surface. This was electric flux, and this was what Gauss's theorem. So Gauss's theorem is always linked with what? The closed surface. Is always linked with the closed surface. Okay. So here the electric flux is equal to 1 by epsilon naught into Q. What is Q? This Q is total charge enclosed within that closed surface. The total charge enclosed within that closed surface. And we can also write this phi electric flux, but this is what? Electric flux linked with the closed surface. So last day we did the formula for electric flux is E dot ds, and since it is related to closed surface, so we put a circle around it. So this is what? The electric flux linked with the closed surface, and this is equal to what? This Q by epsilon naught, where Q is the total charge enclosed within that closed surface. So this is Gauss's theorem, and we did this in the last class, and we have also done the proof of this Gauss's theorem. Today we are going to do is application of Gauss's theorem. Now, in application of Gauss's theorem, we are just going to find out the electric field, because there is the electric field in the Gauss's theorem. So we are going to find out this electric field due to charge distribution. Okay, so we are going to find application means we are going to find out electric field, that is E, due to a charge distribution. Okay, so we are going to find out electric field due to a charge distribution, and just remember the charge distribution. There are two terms. If you see, there will be electric field and charge distribution. So we are going to find out the electric field due to a charge distribution. Now, this charge distribution can either be a point charge, that is in this way, the point charge, that will be a Q, a point charge, or it can be a line charge. Okay, line charge means there will be, suppose a copper wire is there and I have charged that copper wire, so we'll call that a line charge. Okay, so line charge, and I have charged this, and the total charge is, suppose it is Q. Third, the charge can be in the form of a plane charge. This is a paper. Okay, if I charge this, okay, so this will be a plane charge. So plane charge, this is, suppose I have charged it positively. Okay, next, there will be a spherical charge. There will be some spherical ball, okay, and I'll charge that sphere, means spherical ball, and I have charged that. So this is, I have charged this with Q and this. Okay, now this sphere can either be a hollow sphere or a solid sphere. Hollow sphere means what? The charge within, there will be the space within this surface will be hollow, will be free. There will be air, okay, and nothing else. So this space is free, means the total charge only resides at the surface. okay, in case of hollow. But in case of solid, the solid means here there will also be charges. The charges will be distributed within the surface also, because this is a solid sphere. So just the difference between hollow sphere and solid sphere is, in hollow sphere the total charge resides only on the surface, and in the solid sphere the charges reside on the surface as well as inside. Okay, so the charge distribution means the charge will be distributed, either the charge will be a point charge or line charge or plane charge or spherical charge. Okay, and what we have to find? We have to find electric field linked with all this charge distribution. Okay, now so in case in the application of Gauss's theorem, we are going to find the electric field due to these charges. Okay, next. Now, so we knew that our task is to find the electric field using Gauss's theorem. Now, how do we find? So to make it simpler, I have made few steps. We'll follow these steps and we'll find the electric field. So what are the steps? The first step is, okay, the first step I have divided into two parts. In the first step, we'll consider a Gaussian surface. Okay, next, the second part of the first step, specify E is electric field at each surface. Specify electric field at each surface. At why we are writing at each surface? Because Gauss's theorem is related to closed surface, and when I am drawing a closed surface, there can be more than one surfaces. Okay, in case of sphere there will be only one surface, but in case of cylinder, there will be a top surface, there will be a bottom surface, and there will be a curved surface. Okay, this is the sphere. Suppose if I draw this, so there will be, this is in the shape of a cylinder, this is the top surface, the bottom surface, and there is a curved surface. Is that clear? So that's why we have mentioned specify electric field at each surfaces. There can be more than one surfaces. Okay, in case of cube there will be 6 surfaces. Okay, so we have to specify E, electric field at each surface. Okay, next, the second step is calculate E dot ds. We have to calculate E dot ds, because in Gauss's theorem what we have to find? This value, the value of E dot ds, and the total charge. Epsilon naught is permittivity of the free space. This is constant. So we have to find the total charge enclosed within the closed surface. This is Q, total charge enclosed within the closed surface, and the value of E dot ds. But we have to find the value of ds, because we are going to calculate the value of E, electric field, in Gauss's theorem. So here we have to calculate ds. So here we are going to calculate, in other words, make it simpler, E dot ds. We are going to calculate the value of E dot ds and the total charge enclosed within that closed surface. So here the we have to calculate this. In the third step, find out Q. Q means the total charge. Find out the total charge enclosed within the closed surface. Find out total charge enclosed within the closed surface. Okay, next, the fourth step, substitute the values in Gauss's theorem. Substitute the value in Gauss's theorem means, Gauss's theorem is what? This is the Gauss's theorem. See, E dot ds is equal to Q by epsilon naught. This is the Gauss's theorem. Okay, this is the Gauss's theorem. Now, E dot ds. The value of E dot ds we have calculated in the second step. See, this, in this step we have calculated E dot ds. Okay, and we have to find the value of total charge, which we have already calculated in the third step. It means in the fourth step we are going to put the value which we have calculated in the second step and in the third step. We'll put these values and we'll get the electric field. Okay, let's start. So just remember these 4 steps. Okay, the first step is, in the first step, the first part is consider a Gaussian surface. We have to consider Gaussian surface. Okay, I'll talk about this Gaussian surface afterward when I'll start finding the electric field. Next, in the second step, the second part of the first step is specify E at each point. What will be the electric field at each point of the surface, whether it be a cylindrical surface or it is a spherical surface or anything. Next, in the second step, we are going to calculate the value of E dot ds. Third step, find out the total charge enclosed within that closed surface. And the fourth step, we'll put the values which you got from in the second step and third step into the fourth step. Okay, now, so let's start the first one. We are going to find out the electric field due to a point charge. Electric field due to a point charge. So this is the electric field, and suppose the point, this is the point charge Q, positive plus Q. Okay, now here the first step was consider the Gaussian surface. So what is Gaussian surface? Okay, so just remember, I've done this in the class. I've told you all before also. We know that suppose here it is a positive charge, and if there is a point charge, we know that suppose suppose this is a point charge. Consider this as a point charge. This is a point charge. Okay. Now here we know the electric field emanates from this point charge in all the direction. Electric field comes out from here, here, in all the direction. Now, to make a Gaussian surface, we draw a surface enclosing all the electric field lines. Since the electric field lines are coming out in all the directions, so what we are going to do? We are going to draw a surface which will enclose all the electric field lines. Means if we draw a surface which encloses all the electric field lines, it means the surface will be spherical. Okay, so we know if electric field is emanating in all the direction, so if I enclose this surface, we'll get a sphere. So this sphere is considered as a Gaussian surface in this case, in case of point charge. So always remember, in case of point charge, the Gaussian surface will be in the shape of a spherical shell. Okay, so, and suppose you have taken the radius of the spherical shell as r, small r. Okay, now, so the first step was we have to consider Gaussian surface. So let us consider a Gaussian surface in the shape of a spherical shell, and the charge Q is kept at the center, and this charge Q is where? Is kept at the center. The second part, we have to specify E at each point, at each surfaces. We have to specify E at each surfaces. Second part of the first step. Okay, just remember those steps. So the part B will be specify E at each surfaces. Now we know in case of sphere there is only one surface. Okay, so there is only one surface. So now if I consider E over here, so we know that the electric field, if I just remember one thing, for finding out electric field, the point at which we have to find the electric field, we put a unit positive charge at that point. Similarly, we are keeping a unit positive charge over here, and this was a positive charge. So we know that the force will be a repelling force. There will be a repulsion. So electric field will be in the direction of force. So the electric field E will be in this direction. Okay. Now, next we have to consider the area vector. We know that over here the area vector. So in the previous class we have studied the area vector is always perpendicular to the surface. If this is the surface, the area vector is perpendicular. The area vector will be this, my pen. If the surface is like this, area vector will be like this. Means the area vector is always perpendicular. So if I draw a perpendicular line over here, so we'll get this only. So it means the area vector is along the same line as that of electric field. Okay. So here we can write E, electric field is radially outward and making 0 degree with the area vector. Is making 0 degree with the area vector. Okay. So this 0 degree is what? Remember the previous class. EA cos theta. What was theta? Theta was the angle between electric field and the area vector. Okay. So this 0 degree is what? Angle between electric field and the area vector. So this is actually the value of theta. So theta is 0 degree. Okay. Next. In the second step, I have written calculate E dot ds. Means we are going to calculate this. E dot ds. So here it is E dot ds and there is what? A closed integral. Closed integral. So it means we have to separate these into different surfaces. Okay, I'll expand this into different surfaces, but we know in case of a sphere, because here the Gaussian surface is what? A spherical cell. So in case of a sphere, this we can write that E dot ds as E dot ds, and we don't have to provide this close integral sign. Why? Because there is only one surface in case of a sphere. Now E dot ds, this is a dot product, so what we do? E ds cos theta. So it will be E ds cos theta. Now here it is theta. Theta is what? Angle between the electric field and area vector, which we have done, which we have already calculated here. So here we know that theta is how much? Theta is 0 degree. So cos 0 degree, cos 0 degree is 1. So we can replace this by 1. So here we'll be left with E ds and cos 0 degree is 1. Now just remember one thing. Here the electric field is E. What will the electric field over here? It will remain as E. Why? Because the distance is still R. So electric field will remain constant on this surface. Okay. So electric field will remain constant. So we can, if electric field is constant, so we can take this electric field outside the integration sign. So here we'll be left with only ds. ds is what? A small area. Okay. Now if I integrate this small area, we'll get what? The total surface area. If I sum up this small area, integration means what? Summation. So if I sum up these small areas, all the small areas, if I sum up, I'll get what? The total surface area. So it is simple. So E and ds will be 4 pi r square, where r is the radius. Okay, we can say r is the radius, or r is the point at which we are calculating the electric field. So r is the point where I have kept the unit positive charge. Keep it very simple. Okay. Third, in the third step, I have written find out the total charge enclosed within the closed surface. So here in this case, in case of a point charge, the whole charge is enclosed within that sphere. So the total charge enclosed within the closed surface is Q itself. The total charge is Q. In the fourth step, we have to put these values which I have calculated in the second step and third step into the Gauss's theorem. So put the values. So I'm going to put these values into the Gauss's theorem. So E dot ds is equal to q by epsilon naught. This was Gauss's theorem, and we have calculated the value E dot ds in the second step, that is E into 4 pi r square q by epsilon naught. So 1 by epsilon naught, and q is what? The total charge is q itself. So E is equal to 1 by 4 pi epsilon naught into q by r square. So we have sent this 4 pi r square onto this side, so it got divided. So q by epsilon naught was already over here, q by epsilon naught c, and this 4 pi r square came from here. So E is equal to 1 by 4 pi epsilon naught into q by r square. So this is the electric field due to a point charge. Okay, next we are going to find electric field due to a line charge. Electric field due to a line charge. Now this is a line, so just consider this line as a copper wire, and if I charge that copper wire, so we'll call it a line charge. So suppose if I've charged this line positively, okay, so the first step is we have to consider the Gaussian surface. So what will be the Gaussian surface? Okay, so just remember the Gaussian surface. Just imagine that this line, the line has been made with infinite number of point charges. We consider that this line charge is made up of infinite number of point charges. Now we know that for a point charge the Gaussian surface is spherical, because from a point the electric field lines comes out in all the direction, and if I enclose all those electric field lines, we'll get a sphere. So here also we have got a point charge. Okay, here also we have got, so let's see. So this is the point charge, this is the first point charge. I've taken this point charge over here. So we know that we'll get electric field lines in all the direction. Similarly, we have got another point, so I'm making it bit downward. So here again I'll get electric field line in all the direction. But just remember that these electric field lines, this electric field lines is pointing upward, and this is downward. So these two electric field lines will cancel out each other. Again, this is moving downward and this is moving upward, so these two electric field lines will cancel out each other. Similarly, this electric field line and this one will cancel out each other. This one and this one will cancel out each other. So if we see, after these electric field lines cancel out each other, we see that the electric field lines will be in this way. Only this surface will be left out. All the other electric field lines will get cancelled due to the point charge kept below it. Okay, so in this way, for this point charge again we'll get only these electric field lines. The other ones will get cancelled due to the point charge below it. So in this way we'll see that these electric field lines will be, for every point charge electric field lines will be like this. And if I look at this surface, we'll find it to be a cylindrical. Okay, so we can say that here the Gaussian surface will be spherical. Okay, so Gaussian surface in this case is, so we'll write, let us consider a Gaussian surface which is in the shape of a cylinder, okay, but with its axis along the line charge. Okay, so this axis of cylinder is always in this direction and this axis is along the line charge. Next, the second part, we have to specify E at each point. Okay, so just remember here, see, here we have got there are three surfaces in cylinder, as I've told you all before also. There are three surfaces. There is a top surface. Suppose if this is a cylinder, so there is a top surface, a bottom surface, and the curved surface. Okay, so for these curved surfaces, we find that electric field lines, for this point electric field lines will be in this direction and the area vector will also be in this direction. So in case of curved surfaces, if I move anywhere on the curved surface, the electric field, this electric field and the area vector will be along the same line, means the angle between E and DS will be 0 degree. But if I move on to the top surface, so this is the top surface, okay, so this is the top surface. Now this is the surface, okay, this is my hand is my palm is the surface, okay, so my palm is the surface, this is the surface, okay. Now the area vector will be perpendicular to it, so this is the area vector, okay, and electric field lines, so electric field lines are in this direction, so electric field lines is in this direction, okay, and the area vector is perpendicular. So here this electric field and this area vector are making, this electric field and area vector is making how much? They are perpendicular to each other, they are making 90 degree, okay. So here we can say here electric field is in this direction, okay, electric field is in, and area vector is in this direction, electric field here and area vector on here. So they are perpendicular, so they are making 90 degree, and we know that theta is 90 degrees, so the electric flux will be E dot ds, E ds cos theta, theta will be 90, cos 90 is 0. So it means, and if I consider that this bottom surface, again we find the electric field is in this direction, area vector is perpendicular to this is the surface, so area vector is perpendicular, so they are making again how much? 90 degree. So if angle is 90 degree, it means what? Cos 90 is 0 degree, so electric flux linked with this surface, electric flux linked with this surface will be 0. So there will be electric flux only due to the curved surface. Is that clear? Electric flux will only be due to the curved surface, okay, and the electric flux for the top surface and for the bottom surface will be 0. So we can say E, electric field, is making 0 degree with the curved surface, okay. For top and bottom surface, this electric field which is making 0 degree with the curves of with the 0 degree with the area vector, so E is making 0 degree with the area vector at the curved surface, and for top and bottom surface E is making 90 degree with area vector. So E is making 90 degree with area vector, okay. So E is making 0 degree with the area vector at curved surface, and for top and bottom E is making 90 degree and cos 90 is 0. So we won't consider this top and bottom surface while calculating the electric flux. Next, the second step, we have to calculate E dot ds. this was the second step. We have to calculate this. Now first we have to expand this, because this is what closed integral. So if I expand this, we'll get E dot ds. Suppose this is for curved surface, again plus E dot ds for top surface, again plus E dot ds for bottom surface. Okay, so expand this. I have expanded this. In the previous one, during the point charge, there was only one surface, so E dot ds was E dot ds only, because there was only one surface. But for the cylindrical, because here the Gaussian surface is what? Here the Gaussian surface is what? Cylindrical. So we have got three surfaces. Now we have seen that here E dot ds. Okay, see, if I have to write down the magnitude of this, so we'll get what? E ds cos theta. Again here we'll get what? E ds cos theta. Suppose I'm writing theta dash, we can write plus E ds cos theta dash. Okay, now here we know the value of theta is what? 0 degree with the curve, because this was what? The curved surface. So curved surface means what? Theta is 0 degree. For this top surface, what was the value of theta? 90 degree. Here the theta was 90 degrees. So that's why I'm taken this as theta dash. Okay. So we know cos 90 is 0, cos 90 is 0. These two will get cancel out. These two will become 0. Okay. So here it is. So here will cos 0 degree is 1. So we'll be left with E ds, and this ds we know on the curved surface, so E will be constant everywhere, So here E, we can, since E is constant, so we'll take out E outside the integration sign, and here it will be only ds. So we can write E into, and ds is what? Curved surface area. And what is the formula for curved surface area? So see, this is the line charge. Suppose if I take the length of this line as L, we know the curved surface area. The formula for curved surface area is 2 pi RH. 2 pi RH is the curved surface area of a cylinder. The formula for the curved surface area of the cylinder. So here in place of H, we write L. So here it will be 2 pi RL. Okay. So we got this. In the third step, we have to find what? The total charge enclosed within the closed surface. Means the total charge enclosed within that Gaussian surface, that is the cylinder. So total charge is Q. So what will be the total charge? See, during a line charge, we always take lambda, which we call this lambda as charge per unit length. This I have explained you in the class, that lambda is charge per unit length before also. So lambda is charge per unit length, and the total length is how much? L. So we can say the total charge will be charge per unit length into the total length. Okay, it is very simple. See, cost price of 1 pen is 30 rupees. What will the cost price of 3 pens? The 3 into 30. Similarly, charge for unit length is lambda. So what will the charge for the whole length? L. Lambda into L. Okay, so the total charge is lambda into L, where lambda is charge, the lambda is charge per unit length, and L is the total length of the line. Is that clear? Now we got this. In the fourth step, we are going to put its value. Okay, so the value in Gauss's theorem. So this is the Gauss's theorem. E dot ds is equal to q by epsilon naught. The value of E dot ds will get from the second step, that is 2 pi RL. So we can write this as E into 2 pi RL is equal to, and here q by epsilon, the total charge is how much? Lambda L by epsilon naught. Now see, this L and this L will get cancelled, and we have to send this 2 pi R onto this side. So I'll be left with, so see, E will be equal to lambda by 2 pi epsilon naught R. This is the electric field linked with the line charge. So this is the total, where lambda is charge per unit length, 2 pi epsilon naught is constant, r small r is what? The radius of the cylinder. Okay. Next, third one, electric field due to plane charge. Electric field due to a plane charge. Now again, this is a plane charge, and I have charged this, suppose positive. Okay, so next we have to consider the Gaussian surface. Okay, so always remember the Gaussian surface of plane charge, we take what? We take a small area, and in case of plane charge, as we have taken lambda as the charge per unit length, similarly here the sigma, we take notation sigma as charge per unit area. Charge per unit area. Okay, and we consider a small surface of area A, capital A. Okay, now for this surface, the Gaussian surface is also in the shape of a cylinder in this way. Okay, so here the Gaussian surface will be in the shape of a cylinder, but the axis of this cylinder is normal to the plane. In case of line charge, the Gaussian surface was in the shape of a cylinder, but the axis was along the line charge. But in case of plane sheet of charge, the Gaussian surface is perpendicular to the plane charge. The axis of the cylinder is normal to the plane charge. Okay, so again, the first step, let us consider a Gaussian surface which is in the shape of a cylinder whose axis is perpendicular to the plane. The axis is perpendicular to the plane. Next, we have to specify E at each point, electric field at each point. So see over here, electric field. So the electric field is moving in this direction. Okay, now so again the Gaussian surface is in the shape of a cylinder, so it means we have got again the three surfaces: the curved surface, the top surface, and the bottom surface. Here the right surface, left surface, and the curved surface. So if I consider the curved surface first, so we know the area vector is always perpendicular to the surface. So this is the surface, so area vector will be perpendicular. This is the direction of area vector, and electric field is moving in this direction. So area vector and electric field is perpendicular to each other. They are making 90 degree. Now, so for all the area vector on the curved surface will always be perpendicular to the electric field. Next, so we got the area vector for the curved surface. Next, let's move on to this right surface, this surface. For this surface, the area vector will be what? Perpendicular to the surface. This is the surface, this is the surface, the area vector will be perpendicular. This is the surface, the area vector will be perpendicular. And electric field is also moving along the same line. So electric field is also in this direction. So this electric field and area vector are both along the same direction, means the angle between these two now is 0 degree. So for the right surface, the angle between area vector and electric field is 0 degree, and similarly on the left surface the area vector is perpendicular to the surface and electric field is also moving in the same direction. So again electric field and area vector is along the same line. So here we can write E electric field is making 0 degree with area vector for right and left surfaces. Okay, so this is the right surface, this one is the left surface, and this whole is the curved surface. So is making 0 degree with the, and for curved surface E is making 90 degree with area vector. So for curved surface E is making 90 degree with the area vector. Now the second step is we have to calculate the value of E closed integral of E dot ds. So we have to find the value of E dot ds. Now we have to expand this closed integral. So we know this is in the shape of a cylinder. So here it will be E dot ds for the right surface, the surface which is on the extreme right. Next E dot ds for the left surface, and E dot ds for curved surface. Now here it is E dot ds. So to write the magnitude of this dot product, it will be what? E ds cos theta, where theta is the angle between electric field and area vector. So right surface, okay, instead of right surface I am writing here the theta is how much? 0 degree, because here we have seen for the right side here the theta will be 0 degree. Again here the electric field and area vector is along the same line, so again here the theta is 0 degree. So for the right surface and left surface theta is 0 degree, and here ds cos theta, here the theta is 90 degree. So this will be 0 because cos 90 degree is 0, so this portion will become 0. Now cos theta that is cos 0 degree, cos 0 degree is 1. So we can write E ds, and we know that E electric field is constant for a confined space, for a confined surface. For this surface the electric field will be constant. Okay, so we can write E ds okay, this one is 0. Now electric, we can write this as 2 EDS plus EDS, so here it will be 2 EDS. Now E electric field is constant for a surface, okay, so 2 E, and there will be, so we have to integrate only the ds. So ds is what? A very small area, and we have taken the total area as how much? Capital A. So in place of this ds we can write 2e, and in place of ds we will write a. So 2e into a is the value of closed integral of E dot ds. Next step is we have to find the total charge enclosed within that closed surface. The total charge, so we denote total charge as q. So total charge will be how much? So see, total charge enclosed within this surface, okay. So see, we have taken sigma as charge per unit area. So for unit area the charge is sigma. So for total area the charge will be how much? That will be the total charge. So for unit area the charge is sigma. For A area, capital A area, the charge will be sigma into A. It is a simple unitary method. So total charge is charge per unit area into total area, as I have done in case of the line charge. In case of line charge, we have taken lambda as charge per unit length and the total length was L. So total charge was lambda into L. Similarly over here, the charge per unit area is sigma and the total area is A. So total charge will be sigma into A. Next, in the fourth step, we are going to put these values into the Gauss's theorem. So first of all, I write the Gauss's theorem. E dot ds is equal to q by epsilon naught. Now we have already calculated in the step 2 the value of E dot ds. So E dot ds, the value of E dot ds is 2E into A, and here it is 1 by epsilon naught, and total charge q we have calculated as sigma A. So here this A and A will get cancelled. So we'll send this 2 onto the other side. It will be E is equal to sigma by 2 epsilon naught. E is equal to sigma by 2 epsilon naught, where sigma is charge per unit area. Okay, now just remember one thing here: the electric field does not depend upon the distance from the plane charge, because in the expression of electric field there is no r in it, there is no distance. But in case of line charge, it was electric field was lambda by 2 pi epsilon naught. This r, what was r? R was the distance from the line charge. As I move further, the electric field will decrease, but electric field is inversely proportional to the r, the distance from the line charge. But in case of plane charge, in the expression of electric field, we do not have r. It means what? If electric field over here will be same as electric field over here, electric field in case of plane charge will remain constant. It is independent of r, it is independent of the distance from the plane charge. It is independent of it. Okay, so next let's move on to the last part, that is charge, electric field due to spherical charge. Now just few moments ago I have told you all that this electric field due to spherical charge. Now the charge is in the form of sphere, and this sphere can be of two types. It can either be a hollow sphere or it can be a solid sphere. So in case of hollow sphere, the total charge only resides on the outer surface, but in case of solid sphere, the charge is distributed all along the volume. It is also inside the sphere also. Okay, so the first case which we are taking is the hollow sphere, or we call this as spherical shell. Shell means a hollow one, hollow sphere or spherical shell. So this is a sphere, okay, of radius. Suppose I am taking the radius of this sphere as capital R. We have taken radius as capital R. Now we have to find the electric field, suppose over here. So here we can either find the electric field outside the sphere, on the surface, as well as inside the surface. So I can write this into three cases. The first case will be outside the sphere, second one will be on the surface, and third one inside the sphere. So we are taking the first case, suppose case 1, when we are finding electric field outside the sphere. Okay, and suppose I'm taking this distance as small r. this small r is the distance from the center of the sphere. Okay, so this is r. So what will be the electric field for it? So just remember, to find the electric field, first we have to draw a Gaussian surface. So if I draw a Gaussian surface, it will be somewhat in this shape. This will be the Gaussian surface. Okay, it is similar to the point charge. So the Gaussian surface is like this. So the Gaussian surface is what? Is spherical. Next, if I consider E and ds on this point, so E is radially outward and ds, the area vector will be perpendicular. So ds is also in the same direction of electric field. So E and ds are making 0 degree. Okay, now I'm not going to write all the 4 steps again and again. We know that in the 4 step, the first step was, in the first step, the first part was we have to consider the Gaussian surface, and the second part of the first step, it was we have to specify E at each surface. So in case of a sphere, there is only one surface, so we'll consider E, the electric field, only on that surface. So electric field outside the sphere, first case. So we know that for E dot ds, we have what? E ds cos theta, and there is only one surface. And this theta, here E and ds are along the same line, so theta is 0 degrees, so cos 0 degree is 1. So we can replace cos theta by 1. So we'll be left with E ds. Okay, now we know that electric field on this Gaussian surface will be constant everywhere. So we can take this E outside the integration sign. So E, and inside the integration sign it will be ds. Now ds is what? A small surface. This is ds. So if I sum up all the small surfaces, we'll get what? The total surface. And we know the total surface area of a sphere is 4 pi r square. So in place of integration of ds, we will write 4 pi r square, where 4 pi r square is the total surface area of the sphere. Next, total charge. So total charge for the, when the point is outside the sphere, the total charge is this whole charge, that is q. The whole charge is q. And where is this q lying? On the surface. This charge q is lying on the surface. Okay, so the total charge is q. Total charge is q. So if we put these values into the Gauss's theorem, the fourth step, this was the second step, okay, this was the third step, and for the first and second step I'm not writing it again. The first step was we have to consider Gaussian surface. So I have already told you that for the Gaussian surface in this case will be a sphere, and the second part of the first step was we have to specify E, electric field at each point, and electric field at each point is making 0 degree with the surface. So the first step is over. In the second step, we have to calculate the value of E dot ds, that I have calculated over here. In the third step, we have to calculate the total charge, and total charge is q for this sphere. Okay, and next, the fourth step, we have to put these values into the Gauss's theorem. So first of all, I'm going to write down the Gauss's theorem. So Gauss's theorem is close the integral of E dot ds is equal to q by epsilon naught. The value of E dot ds I have calculated, E into 4 pi r square. Total charge is q only, so q by epsilon naught. So electric field will be 1 by 4 pi epsilon naught into q by r square. This is same as the point charge. So when a point is lying outside the sphere, the electric field will be same as the charge is concentrated at the center. Here the charge is not a point charge. Here the charge is in the shape of a sphere. But when the point is outside, we consider this whole charge is concentrated at the center. So the expression is similar to as electric field due to a point charge. See, electric field due to a point charge. This is the electric field due to a point charge, and what we have calculated, E is equal to 1 by 4 pi epsilon naught into q by r square. And here, when the electric field outside the sphere, when we are considering the point outside the sphere, again the electric field is same. So when the point is outside the spherical shell, we consider, or we assume that the whole charge of the sphere is concentrated at the center, and we consider it as a point charge. The whole sphere is considered as a point charge. So the electric field is 1 by 4 pi epsilon naught into Q by R square. Okay, now second case, if I put if I have to find the value of electric field on the surface. So in this case, just we know this r, this distance r, and we know that we have taken radius as capital R. So this small r will substitute it by capital R. So this small r will be equal to capital R for when we are considering it on the surface, when we have to calculate the electric field on the surface. So it will be similar to this. E is equal to 1 by 4 pi epsilon naught into Q by capital R square, where capital R is the radius of the sphere. Okay. Next, third case. The third case, when the point, we are going to find electric field inside the sphere, inside the spherical shell. When electric field is inside the spherical shell, it means, always remember, in spherical shell the charge always resides on the surface. I've told you in the beginning, at the beginning only, the total charge in a spherical shell always reside on the surface. So if we have to find the electric field inside the surface, so always remember the charge inside the surface will be 0, and when the charge is 0, electric field will be 0, because electric field depends on the charge. If charge is 0, electric field will be 0. So in the third case, simply write down that electric field is 0. Why? Because the charge inside the spherical shell is 0. Okay, next. So we have completed the first part, that is the spherical shell one, hollow shell. Next, electric field due to solid sphere. Due to solid sphere, we sometimes write solid sphere, or we can also write this as volumetric charge distribution. Volumetric charge distribution. Volumetric charge distribution means what? Volumetric charge distribution means the charge is spread out throughout the volume. Okay, so this is a sphere. Again, the radius is r. Okay, and the radius is r, and the charge is distributed all along the surface as well as on the surface. Everywhere the charge is distributed. Now again, we'll have three cases. Case 1, electric field due to electric field at the outside means, suppose here we have to find the electric field. So for this, we'll draw a Gaussian surface which will be a sphere, and the total charge of the sphere, suppose you have taken as q. So for this, the total charge will be q, and this will be similar to the spherical shell. It will be same as this case 1. Electric field outside the sphere for spherical shell is what? 1 by 4 pi epsilon naught Q by R square. Similarly over here, for volumetric charge distribution or for solid sphere, the electric field outside the sphere will be same as in case of spherical shell. So I'm just writing down the final expression. E is equal to 1 by 4 pi epsilon naught into Q by R square. It will be similar. The calculation will be similar. So what you all have to do, again write down this step over here also. Okay. Now, case 2. For the second case, electric field, we are going to calculate electric field on the surface, and just remember, on the surface the small r will become equal to the capital R, that is the radius of the sphere, because R is the radius. So electric field will be same, 1 by 4 pi epsilon naught into q by, in place of the small r we'll put capital R. So these two were similar to the spherical cell, but what happens if we move inside? Next we have to find electric field inside the sphere. Now here it will vary. Why? Because in spherical cell I have already told you all the charge resides on the surface. So as we move inside the spherical cell, the charge will be 0, so electric field will be 0. But in this case, the charge is being distributed all over the surface, inside as well as on the surface. So in that case, one thing is clear, that electric field won't be 0 inside the solid sphere. Okay, so we have to calculate this. So electric field inside the sphere will be, just remember this is a sphere. Suppose this is sphere and I want to find electric field at this point. I have to find electric field over here. So what we have to do? The same process. First consider Gaussian surface. So here the Gaussian surface will be this. This will be the Gaussian surface inside the sphere. And suppose this distance is r, small r, because we have taken the radius of this original sphere as capital R. So this is small r. Next we have to specify E at each point. So at this point, what will be the electric field? Electric field will be in this direction. Area vector will also be in this direction. So E and ds are along the same line. So E and ds are making 0 degree. Okay. Now next we can write here that E dot ds, the closing E dot ds will be E ds cos theta, and we know that theta is how much? 0 degree. Cos 0 degree is 1, so it will be E integration of ds, that is E into 4 pi r square. Okay. Now what will be the total charge? Total charge Q will be how much? So just remember, during volumetric charge distribution we take a notation rho. Rho is charge per unit volume. Charge per unit volume. Rho is charge per unit volume. Now here the total charge will be, suppose the charge per unit volume is rho, into what will be the volume of this sphere. So we know the volume of the sphere will be 4 by 3 pi, and this distance r, 4 by 3 pi r cube. So 4 by 3 pi r cube is the volume of this sphere, this Gaussian surface, and rho is what? Charge per unit volume. The charge per unit volume into the total volume will get what? The total charge. Okay, so the total charge here in this case will be rho into 4 by 3 pi r cube. Okay, now next we'll put this value in the Gauss's theorem. So the Gauss's theorem is E dot ds is equal to q by epsilon naught. So E dot ds is equal to what? E into 4 pi r square, and q is how much? Q we have found out, rho 4 by 3 pi r cube. This is q, and epsilon naught. Now see, this r square and this q will get cancelled, so here we'll be left with r only, and this 4 pi and this 4 pi will get cancelled. So E will be equal to rho r by 3 epsilon naught. This is the electric field due to volumetric charge distribution, or due to solid sphere inside the sphere. Is that clear? Okay, so see,